Welcome. Welcome to the closing episode of 2021. I was looking forward to it for so long, which is kind of interesting because in a way I'm literally most qualified for this episode than for any other one, but it kind of makes me slightly more stressed and nervous. Uh, we will talk about microservices today. I will try to not get too derailed to other topics such as Kubernetes, containerization, Terraform, cloud, and stuff. Even though, to be honest, in my head, these topics kind of are close to one another. But I'm doing my best to keep episodes under 1 hour. So let's hope it works out this time. The plot sandwich. If you know what this appeals to, don't say it out loud. Otherwise, you might be in trouble. The plot sandwich is the following. The current trend of going towards microservices is, I think, a really, really awesome idea. It's the right thing to do. It has a small-ish number of downsides, which we will cover today. So hopefully by the end of the episode, you will be more equipped with avoiding those issues. And it still is the right thing to do. Don't get me wrong. We are doing the right things for this planet by designing stuff in microservice ways and making the job of software engineers better over time. At the same time, yes, I do feel that sometimes people get carried away with their desire to build things in a microservice fashion, and good senior plus engineers and architects have the moral duty to ask those people to justify their decisions and sometimes push back. And in this episode, we'll try to get to the common ground, to the productive common ground. I wanted to start by outlining some worthy reasons for microservices. And I was really thinking what's the best way to start, because I have some picture in my mind of how things are supposed to work in the world of engineering, and I'm going to try one of the approaches, one of the ways I view this, and let's see if it sticks. So this approach starts from a simple assumption: the true goal of an engineering organization is to ship and support the software that works. It's that simple. There's nothing else software engineers should do. Well, most of us. We just need to ship software that works and be able to maintain it, be able to extend it, and be able to troubleshoot it if it goes wrong. When the company is small, when the team is small, this kind of happens organically. There's really no extra skills, no special effort is required in order to ship and support the software that works. But oftentimes, what really happens is software engineering teams grow unexpectedly, grow suddenly. It's not the issue that they grow. The issue is that they grow suddenly. And when a team suddenly grows, when it goes through this hyper-growth phase, oftentimes shortcuts are taken, mistakes are made, and these mistakes are costly to correct later on. When multiple teams, multiple people have to work on the same product, coordination is key. And I think I was trying to outline a couple of things where coordination is really important, as in expensive if not done right. In my personal list, mutual understanding, shared understanding of the data schemas and the APIs, that's a really good thing. Well-defined team boundaries really help. End-to-end tests, we'll touch on this again in the future. I'm a huge fan of end-to-end tests, and I think it's the right thing to do, to run end-to-end tests when they touch, with these tests touching multiple parts of the system, as opposed to every team saying, my thing works, it's on your side. And of course, so we have a huge company, huge organization. You need to be able to roll out code in some partial-ish setting, because, well, that's oftentimes what is desired by the upper management and by the top SREs and DevOps. We'll touch on this again. Just the point is, all these things are really good. And all these things are, in the minds of most engineers, highly positively correlated with moving towards microservices, which is perfectly fine, don't get me wrong. I just want to make it very clear that it's not always the case that going to microservices is guaranteed to fix these things. And it's not always the case that microservices are the only way to fix stuff. here's the extension of my mental model of why are we, as the IT society, why are we at where we are. I think the truth is very simple. Of all the industries on this planet, IT is the most scalable one. Like part of the reason top engineers are paid so much compared to other professions is extremely simple. If you manage to improve some piece of code by a tiny percentage, like 0.01%, but this code is run billions of times per day by billions of people on the planet, which is not impossible in software. And clearly, you're making a huge impact. That's just how it is. So much like the Industrial Revolution, 150 to 100 years ago, has changed how physical stuff is made. The digital revolution is shaping how much of an impact can people have. And IT is one of those industries where the impact is unbounded in a way compared to most other industries. Which is awesome, which is cool. The sad truth is that I like the analogy here with poker. When you play in a poker tournament and you've been sitting at a table, you cannot leave. You have to play with these people for a while until the table is broken. And what you would often see at a poker tournament is that somebody, usually one person, plays a lot more than others. Now, mathematically speaking, it's a mistake. If people are playing weird hands all the time, chances are that in the long run you'll take their money. But the truth is, statistically, once you are going to play your hand, you will play with these people. So it's important to study the players you're playing with, but it's more important to study people who play more hands. Like on the one hand, you know they are wrong, but on the other hand, you'll engage with them more often just because statistically, once you decide to play, they will also play. So what it means for us software engineers is that many companies are hiring. A huge, like all companies, how do I put it, in a way I'm comfortable with in public. It's an open secret. It's well known in the industry that all the top companies, all the FANG, and all the overhyped, overfunded Series B, C, D startups, they have extremely ambitious hiring goals. Like they literally want to grow like, by some huge factor, like this year, next year. So, and because of the basic laws of statistics, of 1,000 people who will change jobs or get into the job in IT, of this 1,000 people, 900 something would end up working either in large companies like FANG or in large hyper-growing startups like Mixpanel, Amplitude, GitLab, you name it. And now view the same process from inside the company. You know you need to grow. This decision was made. Nothing's going to change. You will grow. When you're growing at this speed, when you find good people, they're rare gems. You're going to keep them, retain them, cherish them, give them bonuses because they're really nice to have. But most people would be, I would say, slightly below the senior level. Like the average level of your hire, if you want to grow super quickly, will be below senior. That's normal. That's just life. If you decide you should grow extremely quickly, you most likely can use these people effectively so that both these people and your company benefit from this engagement. But the truth is, somebody has to help these people to be productive. And people below senior level, people somewhat below the senior level, one thing they are statistically not good at is working with other teams. It's not hard. It just requires special skills and experience to understand where pure technology, as in writing code, hits the boundary where you have to go to working with people, and then you need to establish processes so that this collaboration is effective. All I'm coming to is that when a company declares we are microservice friendly, it's a safe and cheap way to declare that the goal of a company, the strategy by which we grow our engineering organization is to make sure the teams can be more and more decoupled. So if you are joining this company and a specific team hires you, in a way it benefits both you and the company that this specific team that hires you can be productive in this team and ship useful software, not having to be exposed to the rest of the work. So that's, in a way, that's exactly what microservices are. You are joining the team, the job of which is to develop a specific microservice or a few microservices. There's a constellation of those in the company, hundreds and hundreds, and you would like to work, like you will work on one of them and maybe touch 3 or 4 more. You would, of course, touch something standard like authentication and load balancers, maybe like front-end level. But overall, we need to have the like industry-wide, planet-wide process by means of which people who don't want to get exposed to the whole complexity can still be happy and productive. And microservices, on the grand scheme of things, are presumably solving exactly this problem. So honestly, unless you believe in some huge market crash or the world changing dramatically in the next 5, 10, 20 years, like AI taking over or the next Stone Age, which I think is highly unlikely, this trend is most likely going to continue. Now here are the bad things about microservices as an approach, as a philosophy, as the top-level strategy. The bad thing is that when you do your best to eliminate cross-team dependencies as aggressively as possible, you literally cut them down. You say, hey, you used to be one thing, now you're 2 or 22 different things. When you cut this dependency, you solve some problems. You solve some problems because standardization of cross-team collaboration has to emerge faster than it would have otherwise. So you would kind of make people have to talk to each other about data pipelines, about APIs. You have to have processes how to test components that talk to each other instead of being one single large component. Microservices oftentimes come in a package with Agile Scrum, which means you probably will have Scrum Masters, which again is only fair because these people can speed up the process and they are much faster to train than engineers, and there are more of them on the market. And Scrum has tons of benefits. Agile done right is an awesome power, and one of the benefits it brings is that people don't get blocked last minute. You're presumably supposed to know, to understand who is blocked by what early on. All good things. All good things. The bad thing is that when you do it this way, you create other problems that are actually substantial. They are huge. They're not as visible and not as sexy. So somebody is working on those, and you often don't know who is working on them, and these people are slightly unhappy or extremely unhappy. So the ugly part is what these people are, and who these people are, and what they do. And the simple truth, I think, like from my experience, quite extensive to be honest, I think I'm qualified to say it's the truth. The simple truth of today is that when a company is going through a top-down push towards microservices, what it does is simply pushing their responsibility of making the whole thing work together as one. This responsibility is pushed down the line, so that it's no longer like the head of engineering, executives. It's down to individual team leaders, down to individual architects, and these people suddenly have a different job to do. Simply put, unless they do step up, things just won't work together. And I had to step up in multiple roles. Architects become extremely important. Technically, I am one, so I feel the pain. I can tell you a lot of stories and how to deal with that. The work of a DevOps is suddenly a lot harder because it's not just about running one thing in production. It's about running tons of things that talk to one another, and they're not always perfect, and they fail at in all unpredictable ways possible. And it's presumably your job to make sure they don't fail. So that the role of a DevOps in a modern, recently containerized and microservice architecture is very hard, trust me, especially in the modern cloud era where not everything is so stable as it should be. You have people who are responsible for making sure the build is streamlined, so developer tools are no longer as simple as they used to be. You need to work with standardizing and streamlining the ways people just work with code from the same GitHub flow, if you wish, all the way to how you run the tests, how are Jenkins machines configured, how do you search the code, and all those minor details. And since what we're trying to do is enable people who are slightly below senior levels, suddenly those who understand how to connect the dots between the business goals and the code being written, suddenly these people with product mindset are extremely important, because ultimately it's not about how your code works. It's about what its functionality brings to the end user. Oftentimes, the correctly asked question about the behavior of your code is exactly what the company needs. Like, there are tons of examples from real life products, from mail to Uber-like taxi companies, such that how do you look for the best driver for the rider? What should the algorithm look like? Well, there are tons of shortcuts to make and tons of optimizations to make, but fundamentally they should not come from engineers who know how to optimize data structures. They should come from product people who understand what is the user's expectation. And my main point here is that all I've just talked about, these are full-time jobs, which I think is perfectly fine if somebody decides to step up and do this job. That's wonderful. In most cases, companies do appreciate it. But what I think is not fine, which is what is suboptimal, is that those people and this work being done behind the scenes is now presumed to be taken for granted, such as, oh, you guys use microservices? Well, good. I assume you have this and that. And if something doesn't work as people expect it should, people get unhappy as if the company owes them for all these processes to work correctly, which, like, in a way, it's true. It would be awesome for a sub-senior hire to expect things to work correctly, and they will be correctly upset if things are not working as they should. But they never do. And microservices as a religion, as a dogma, is a sure way to the world where things would not work correctly quite often. People will be unhappy quite often. So the plot for this episode is the following. I've put together some list of most common reasons for microservices, which, again, I'm not saying they're bad. They might be good reasons. But if you take one thing away from this conversation, take this. People who use these kind of arguments with no full justification, how do I put it mildly? They are the risk the company carries. So that these people being listened to without justification, they carry the risk. They are the bearers of the risk that the company is going to do things wrong, which would cost the company a lot of time and money down the road. So I'm just going to go through each of these dogma in a few words, and then we talk about how to reasonably argue on these topics. So one of the things I hear very often is that each microservice should have its own database. It sounds so good in theory, like so good. My microservice, my Redis, my Postgres, my cloud database. I don't care about your data, your schema. I just have my own thinking. When you do it this way, what actually happens is, at some point in the future, you need to make a transaction. You need to make some atomic change to the state of the data in the whole company that affects your data and somebody else's data, someone else's data. Which certainly is a lot less easy than a single SQL update that happens transactionally. And there's no shortage online of tutorials, blog posts, and videos of how to do compensating transactions, or how to emulate two-phase commits. There's this wonderful thing called the saga pattern that kind of solves the problem. But I want to point out that this problem technically doesn't exist, as long as what has to be mutated atomically, simultaneously, lives within a single relational database. And if you know me well, you know I'm not a fan of RDBMSs. Honestly, I don't think they are the future. But they are so good at handling metadata, they are so good at transactions, that, yeah. Any questions? So yeah, to conclude point number one, when people are religiously talking about separating databases per microservice, ask them why are they trying to reinvent the wheel for the n+1st time. The second big point, which I also hear a lot, is let's separate the code of microservices into different repositories. So team A is working on microservice A in their own repository called A, and team B is working on B in repository B. Which, of course, this absolutely makes the job of teams A and B much easier in their daily life, because no one's going to break their build. Their own test will probably pass. They would most likely be able to configure their own CI/CD pipeline that uses some mocked or shimmed inputs from potential other services their service has to talk to, all good. But then, again, it's never hard to make a change that is self-contained within a single small component. The complexity always emerges from different pieces of software and different teams talking to one another. Conway's law comes into play here right away. And then my personal quirk here is, so imagine you run a team, I run a team. We need to make the change that affects both teams. So maybe add an extra field or extra API call on my side, so you call it on your side. All good. You make a change, I make the change, we test it. Maybe each team is, 4, 5, 8 people, probably no more than 8. So somebody from my team, maybe me, someone from your team, maybe you. You guys, we step up, we communicate, we make this change, it works. But then the code path, the code history, the commit history of my team's repository and of your team's repository, they tell a consistent story. We were requested to make this change, we made it, it works, here's a test. But the knowledge that this change in my team was made to support this change on your side and vice versa, this knowledge is lost forever. It only exists in our heads. Like, you will probably have it in Jira or in some Confluence wiki page or in some Google Doc or Miro board. But the truth is, if it's not in the code, if it's not visible for everyone right away, it's what's going to be lost. And this knowledge is important. At some point down the road, a year or two later, somebody would ask, why do you have this endpoint that is almost identical to that endpoint with slightly different semantics? And in order to simply answer, oh, it's because those guys asked me to do it this way, had you known it right away, you would have been able to make better decisions as a company, as a team, as a business. But because we're all microservice friendly, quote unquote, this knowledge is lost, and we have to redo things and lose this knowledge. This ties tightly to the third point. Again, one of the religious dogmas is that when we change our microservice, you don't need to change yours. And don't get me wrong, backwards compatibility is an awesome thing. In fact, microservices, when they are introduced so aggressively into this world, microservices made forward compatibility more important. People suddenly talk about it, which I think is awesome. Nobody was talking about forward compatibility 5 years ago. Everyone talks about it right now. So that you should assume that when you roll out your code today may have to communicate with your code written 2 weeks ago, however frequently your build cycles are, your release cycles are. In theory, these are awesome things. If you build your code correctly, you don't have any issues, and you test it all through, you have some canary deployments that test it on real traffic, all good. In practice, it's just extra work. Oftentimes, it's absolutely necessary extra work, because had these two services been in a single repository or even in a single component, you would not need to do any of this. It would just work right away. So yeah, I think what I put here in the slides is that if you try to strive for not requiring changing code simultaneously in multiple places, you're effectively delaying your end-to-end tests up until the very end, up until the last stage, up until the pre-deployment phase. Whereas most good engineers agree that if my code depends on yours, I should test my code against yours as soon as possible. That's how issues are found. If you want to add the feature for me, maybe you want to add a test that makes assumptions about my code. And I would add a test that makes assumptions about your code. The sooner we connect and talk about these assumptions and talk them through, ideally in code, the better off we are as a company. And this often goes horribly wrong. This takes me to my next point, which is my personal pain point all the time, about data schemas. I know I'm biased towards strong typing and all that stuff. I know that's like schema on write, not schema on read. I know I'm like off center at this point. So take my word with a grain of salt. It doesn't have to be the case. But I think when people try to make schema agnosticness of their service the goal, not the means, things break. It's just not a good goal by itself, I think. Oftentimes, the fact that your code doesn't break if some weird JSON or XML is being pushed, the fact that your code doesn't break right away may actually be a bad thing, not a good thing. In fact, I would prefer my code to break as soon as possible if it's being sent requests that are deliberately against what should be sent. By break, I don't mean like destroy the whole system. By break, I mean return an error, not try to make guesses. Again, it's a very long, to be honest, philosophical conversation. How strict should you be? And in some places you have to be strict. In some places being strict is just a bad idea. But overall, I personally found it to be absolutely true that people who are extremely pro microservices tend to be the people who are extremely pro loose data schemas, which in my experience just delays problems instead of highlighting them early on. The second to last point is performance via caching. It's no secret, everybody knows it these days, that databases are slow, and if you cache data correctly, the good, well put, well-designed cache can decrease the database load by a factor of 100, which is huge. What people tend to forget is that cache invalidation is literally impossible to do correctly. So once you cache something, you should ask yourself immediately, what if my cache is no longer valid? Obvious example is something related to security. So if you're logged into the service, and I'm going to return you the data because I know you're logged in, but then you have been a corporate user and you've done something wrong. Maybe you're leaking the data. So you terminate it, your access is revoked, permanently or until we figure out what's going on. Clearly, when your access is revoked, my service shouldn't return you the data because you're not supposed to see this data. But if I have my token and permissions for you cached, how the hell would I know that I'm not supposed to return you the data? So to do it right, you need to have pub sub buses with guaranteed message delivery, with every single service updating this message on the fly. And then suddenly, what if you're not like fully access revoked, but some permission is being taken away, and maybe this permission plays like a second order role in some rule evaluation. So again, to invalidate this cache correctly with all the parts moving, because these permissions are also subject to change version over version. It is really, really hard as in terms of engineering work, testing, and error proneness. So when people say, "Oh, yeah, it's slower if I have like my microservice would be slower compared to a local database, or like talking to the same database from multiple places, but I'm going to put my own cache here and I'll be safe." You will not be safe. You might ship sooner, but you would not be better off in the long run, trust me. And yeah, the last point here is about backwards and forward compatibility. It's awesome if you can afford to ship software that is backwards and forward compatible. It's just, again, oftentimes it's too much work for no good reason. I'll talk about this in a moment, but think about it carefully. Why do you really need to support multiple versions of your code running concurrently? Is it the business requirement, or is it just because you would rather do it this way because it looks cleaner in your architecture? If you need to support obsolete clients for dozens of years, like if you ship physical devices, I don't know, microwaves, they talk to you via some protocols over the network, and you cannot upgrade firmware of this microwave remotely because it's too hard for you somehow, then yeah, maybe this microwave is supposed to last for 10 years. So for all the 10 years, you have to expose the API compatible with this particular microwave, even if there are only 3 in the world that keep using it. But in practice, with the modern world, if your users are using a web app, like a browser-level app, well, first of all, they can always refresh the page, get a new version. Second, most well-done front ends would actually make it refresh automatically behind the scenes. You wouldn't even notice it. So what is the rationale behind arguing that every single version of your code can potentially be up and available out in the air? Why not just say, I'm going to run my test locally? Maybe T as in the letter T is the word used to describe that you're like taking the data stream and putting it into 2 places. So it goes like, it's like a T letter, the split of the flow. So you can T the traffic. You have production rollout, you have incoming requests. All of them go to production, but you also send them somewhere else. And the somewhere else is your future cluster that you are testing. It doesn't serve real GET requests, but it's trying to make sure it doesn't doesn't die under the load, and you can run some regression tests to make sure what you could request from it returns correctly. And then once you know it's working out just fine as it should, you can just do an atomic flip. So if you have 100 machines running the same code, we're all in the cloud these days. 100 machines are cheap. bring up 100 more machines, make sure they work just fine with the new version of the code, do an atomic flip, tear down the old machines. Done. Oftentimes, this is a lot easier than saying we need to make sure we first flip one or two machines from old to new and double check that the new API doesn't kill us. The memory usage should be the same and the traffic load should be as good. Sounds wonderful on paper, but oftentimes it's just a lot more work for really no good reason. I had a few points to make here, to be honest, but I kind of forgot them. So I think this 6 should cover it. If there are no questions so far, I guess I'll proceed. What I'll do right now is it's going to be 3 extra slides because I could not fit it into 1 or even into 2, with the best way to, in my experience, politely ask questions that make people reconsider, or at least think about whether their push towards microservices is justified or dogma and hype driven. I cannot guarantee you my arguments would work, but I think it's, given I do it all the time, it's a major part of my work. I'm hoping that people who listen to us would also learn something. Full disclosure, I have personal goals here. First of all, I want to make sure, I want to get more reference points as to whether my arguments do work. So, of course, try them on your own risk. But if they do work, let me know, please. If they do not work, let me know as well. We'll come up with the better ones, better counter arguments together. And if I'm wrong, I always love to learn. Where exactly am I wrong? Slide 103, best practices. And again, by best practice, I don't mean it's always better to be done this way. No way. It's just I'm trying to outline another possible way to look at the problem so that it makes you think of it from a different angle and ask different questions which may not have been asked before. So one best practice I always talk about is if you need atomicity, if you need consistent updates, so no tri-state, nothing in the middle, that's exactly what database transactions are for. RDBMSs, like them or not, I have my personal quirks, but if it's just metadata, if it's not hundreds of megabytes of data, if it's literally metadata as a single column or a single JSON or whatnot, most databases these days can handle, I would say, 50K to 100K transactions per second, at least. You can configure them to handle more than that, which oftentimes is all you need. You can, in most cases, you can shard your data. So the way it works in the real life is there is some sensitive data that is important for all the users, like authentication stuff. But then you can always shard your data by some content ID, like author ID, post ID, album ID. It's a bit tricky with messengers when you have group messages and a group has 1 million people, but fundamentally, even that can be scaled. So the point is, if you can shard it correctly in the transaction, the atomic change should only touch a few bits and pieces to the degree that the frequency of atomic changes for this particular part of data is literally under 10,000 per second. Put a simple SQL database there, and you get all the requirements you need for free. I'm not saying that's the best solution. You can use like DynamoDB transactions in Amazon. That's fine too. It's just, again, if you need to change three things at the same time and guarantee certain preconditions are met, if you don't do it in a database, in a relational database, you have to reinvent a lot of wheels, and you would most likely either spend a lot of time or forget some corner cases, or both. If you cannot afford to have the database, like a relational database there, the second safe solution, it might even be the first one, to be honest. I like it almost, I wouldn't say I like it more than putting a small SQL database there. What you can do is put a replayable log, such as single topic Kafka. Single topic, because I want the transaction IDs, the requests to be sequential. Like, it's called serialized, but it's a bad word because it has so many meanings. Serialized as in index stamped, 1, 2, 3, 4, etc. If you have some entity that puts these indexes, then your backend can just take this index stamped set of tasks, list of tasks as the task queue, and execute them one by one in however pace it wants. Because what can possibly go wrong? Your queue is suddenly full, and it takes a couple seconds, not milliseconds, to run through. If it happens once a month for a couple seconds or minutes, no big deal. But what you get, like the biggest point I'm making here is that logically, once you have this index stamped correctly, you shrink the place for room for errors dramatically. You can always process this stamped transaction in whatever order you want, maybe multiple microservices talking to one another, because if something goes wrong, you can always roll back and reapply it from the same index. So as long as you have a single topic Kafka, single topic, because if it's multiple topics or multiple partitions, the relative order is not guaranteed. So you have vector clocks, like sub-partitions, multiple partitions of the same topic could go like one ahead of another and then vice versa. If it's a single topic and you can afford to stamp indexes, just do that. And then the other service, in a secure as fashion, asynchronously, takes this input and replays this requests, these transactions or whatnot. I mentioned secure as. Saga is pretty much this very idea with whatever transactions you have to run, having an external orchestrator that just talks to all the services, microservices involved in this transaction, and orders them to first do as much of a pre-check and pre-commit as possible, and then just sends a final sign-off. All right, looks like everybody's on top of things. Let's make this change. If you want to understand Saga, think about multiple Git branches being pushed together. You first do work in your own branch, like 5 of us do work in 5 different branches, then we merge them together. We can do all the work in our developed branches, and then some entity outside would tell us, yeah, all of your branches can be merged to the main branch. Or they would tell us, hey, there's a conflict, try again. The entity that orchestrates this, you're good to go, you need to reapply the thing and try again, and then finally commit. This entity is the Saga orchestrator. That's it. Best practice number 2. If you think in the microservice you depend on is always up and running, it's a recipe for disaster. Because eventually, the microservice-based architecture is supposed to be more durable, more reliable. It's supposed to be up 24/7. Parts of the system die, the system works. The canonical example is if you watch a Netflix show and somehow their recommender engine is down, you shouldn't care. You're watching the show. But then you would quickly see that in the real life, you depend on multiple services. There are bottlenecks. Again, authentication is one of them. Like global load balancer, data store, like statistics. Suddenly, if one of them is down, way more than one service, way more than one user-facing part of the system is unavailable, which is super painful. So unless you can design your microservice so that the other microservice failing doesn't really kill you, you're no better than shipping a monolith with that service. Again, there are tons of good reasons to make it a microservice, like communication patterns and stuff like that. But if you cannot afford, like if you have a hard dependency on another service, so that if it dies, you die, at least be fully aware that in terms of durability, your microservice first architecture is not making things better. It's making things worse. Best practice 3. If you do need transactions across microservices, which is what we talked about in bullet point 1, persist on both ends. Persist as in make sure that if at any point in time your service or another service, if they die, like fully, completely die, they explode, the hard drive is no longer available, there's no network, no nothing, you don't lose data. There's one pattern that I really like. It's called transactional outbox. Again, it applies to databases that support transactions, so most often are DBMSs. It's the idea that if you make an update in some part of your data, and some other service may need this update in some sequential order, within the transaction where this update is being made, in the same database, it can also be put with some journal ID, like sequence ID, into a different table object partition. So that because your database is transactional, the change itself is atomic. Either you change the data and journal this update, or you don't make any changes. And since this journaling is going to be like auto-increment columns speaking in SQL terms, all other services can just say, oh, you know what? Last time I was up and running, I have consumed everything up to the index 1, 2, 3, 4, 5, 6. So please give me all the data that is changed since 1, 2, 3, 4, 5, 6. And then maybe you have like 5 subscribers, and then when all 5 of them have caught up to a certain index, you can erase this data that is now consumed by all the clients from your main database. It's a bit like, yes, replayable Kafka. It's just slightly less work on the side of the entity that actually makes this first mutation. Important reminder here, exactly once is not possible in practice, ever, unless the entity that actually makes the request knows how to re-request correctly on the issuer side. So when somebody tells you, oh, it's so important to have replayability here, I'm going to put Kafka, because Kafka can give me a guaranteed 100% guarantee of exactly once delivery. This is just not true, because you can make an API call to publish something to Kafka, and then everything dies. There's no power. Both machines died, and you cannot consume the response because your machine died. Did it get written there or no? You have no idea. You probably say, hey, I'm going to write it again if I didn't get a confirmation received, and I'm going to have some request ID, idempotency token, so that on the receiver end, later down the road, once everything is back to up and running, I can see, oh, it's the same request being written twice, so I ignore the second one. Wonderful. I'm in a bank application. I'm going to send you money. I type in $100. I say send. Everything dies. Later on, like in the next, let's say, 2 minutes, I open the application again. How do I know if the money was sent to you? There's no strong consistency guarantee. It may have been sent. It's just not deducted from my account. Or it may be deducted, but it's not for you because the details are not populated yet. So if you really want to have exactly once guarantee, you need to make sure that the very issuer of this transaction, in this case me, would say, I'm going to send you $100. Here's why I'm sending it. Here's like a magic token. And I have the commitment from my end that if something dies and I have to try again, I put the same token. So this idempotency token should come from the very issuer of the transaction. It's actually not too hard in practice. If it's like a web interface, I can have multiple steps in the browser, and I put some word describing the transaction later on, and then it's persisted first, so that if everything dies, next time you log into the bank, it would first tell you, oh, you have not completed these transactions. Would you like to finish them? But it has to start from the very user. It has to start from the human being making this transaction, or from the service that initiates the transactions. That's technically how smart contracts work on a blockchain. But it's a different conversation. So yeah, the bottom line is exactly once it's an awesome idea. I love it. Kafka gets pretty close to that, if it's a single partition, especially single topic. But if someone tells you that, oh, I'm going to use Kafka and that's a guarantee to exactly once delivery, be careful with those people. Chances are they are ignorant in more than this one way. Part 2 or 3 of best practices. Again, this is something I personally have to work with quite often. In fact, as recently as 2 weeks ago. End-to-end tests. If I have 2 teams working on 2 different parts of the system, it's tempting for each team to, so let's say these 2 services, they talk to one another, and I work on this team. It's tempting for my engineers to say, you know what, we don't want to depend on those guys for the tests. We have some shimmed, recorded, journaled list of example responses from them. So we can test our service under the assumption that this service works correctly, and our tests pass. Sounds like a wonderful idea, but in fact it's CYA, cover your ass. You just want to pretend that you know what's happening, and you want to have a simple way of arguing that my code is correct, the problem is on their side. They may have a bug in their code, which you have recorded, and your code works correctly, assuming that bug is still there. They would fix it without notifying you because they fixed the bug. And they cannot talk to everybody that talks to their service. They just fix the bug. And then suddenly your tests still pass, but the product fails. Hopefully it's going to be caught later down the road before production in the end-to-end test phase. But what I always say is, we live in the 21st century, and chances are if you use microservices, you use Docker containers or stuff like that. So chances are, this is my team, this is your team. Chances are your team has some quick way to spin up a test container, test backend. It would literally take under a second for something simple to be up and running. In fact, chances are you have something that you run in staging. Like in a data center, physically, there's always a test service I can talk to, and your team is committed, is responsible for making sure that test thingy is up and running. Why don't I make my team run tests against your trunk, your head of your main branch? That's just so obvious. The pain point, of course, is what if you guys break something, then my test would fail. In which case, I say, awesome. There was a potential issue which we caught early. Like you could potentially spend, I don't know, 1, 2, 3 hours every other week fixing this, changing this, and you would say, hey guys, you broke our stuff. You cost us this much time. Fine. They will take you out for beers at company's expense. All good. But again, if you run away from the problem, it would just hit you later in a far more painful way. So like when the service already is there, it's like a Docker container being shipped per commit hash, and you can always spin it up within a single command and tear down with a single command. Why don't you run your tests against that thingy like all the time? That's what I always recommend. And I'm still confused why people keep arguing that, oh no, these are end-to-end tests, we have regression tests. Regression tests, they're only about working with synthetic responses. I know the words. I'm in the industry for a long time. We can talk about the difference between these two. But really, I don't care. Like, if you call them end-to-end tests, make them end-to-end tests, because that's just better in the long run. Atomic swaps, the second bullet point, we kind of talked about it. My main point is, it sounds so cool in theory that you have like 100 machines and you can upgrade them one by one. So you upgrade like the first one and then the second one, and you watch if these 2 machines of 100 are still doing their job while the other ones are still working, and just in case you can tear those 2 down and 98 will still hold the traffic. That's such a wonderful idea, except it makes you have to work a lot harder to guarantee this backwards and forward compatibility. And atomic swaps are actually fairly simple to execute, to orchestrate, especially if you already are containerized and in the cloud, so you can always spin up 100 more machines for a couple minutes of intersection. So these 100 machines you had before, you spin up the new 100 machines, you swap, you tear these ones down. For 15 minutes, although in practice will be more like for 3 minutes, you had both sets of machines running. Your deployment has cost the company another $47. Who cares? It's an investment into better productivity and better teamwork. So as long as you can save this engineering pain by costing the company some negligible amount of money, I highly recommend that. Especially, I had to put it here as a bullet point, especially if the APIs are versioned. In fact, I'm actually against versioned APIs. It's a whole different conversation. Like, if it's a RESTful API, then the idea of putting /v1, api.something.com/v1/something is just wrong. It's not RESTful. Use hypermedia. Use self-descripting URLs and methods and possible actions that the the resource itself tells you can be done against this resource. That's how hate OAS is supposed to work. But yeah, given the APIs are versioned, atomic swaps are just come naturally. Because if you change the API, you just add a new version, flip, and then tell all the other people that a month from now the older version is retired, the new one is this guy, and the only change they need to make is this change. So please make this change until, I don't know, July. In a perfect world, by D. Korolev, it's in a single repository. So I'm just going to declare something deprecated. People will start getting build warnings. And then I rename it into deprecated underscore, and they get build failures. Unless they actually put deprecated underscore there, which I can let them do if it's only for like a week or 2 because their retirement is a month from now. But like it either doesn't build or it builds and is guaranteed to work. That's my preferred solution. The last bullet point here is sidecars. I'm assuming most people these days, especially you guys, know what sidecars are, but it's worth mentioning what they are. A sidecar is when you ship a microservice But the way to talk to this microservice from another place is not by making a network request to your service. It's by making a network request to a small proxy-ish service, which is supposed to run on your machine. So the benefit of this is that I don't ship one thing, I ship two things. I ship my service and the means to talk to it. But the means to talk to it can be distributed across all or multiple callers. So if there's like some caching logic, I can put it there on the client side effectively, even though this client side is not built into your code. So it's still a microservice. I don't mess with your code. It's still, so it's not part of your code, it's part of my code, but physically it's not part of my service. It's part of a different binary, a different process on a different machine. That this single thingy on a different machine is called a sidecar. In a perfect world, according to me, you don't have sidecars, you have clients-side APIs. So you don't expose API as in make this HTTP call to me and here's the resource path and I'm going to give you this headers and JSON fields back. Or here is my gRPC signature, use this call. In my perfect world, if it's high performance, low latency thingy, I built my service and the API, client API for it. And you have to build into this client API into your code, which is a strongly typed build, of course. So if you call the wrong method, it won't compile on your side. And then I can always upgrade this client thing and upgrade my own thing. So this way, if, for example, I used to have like an HTTP interface, like HTTP gets and posts, REST-like interface, and then I changed to binary protocol, and then I changed to maybe gRPC tomorrow, and then it used to be a request response, and now I have a persistent connection. Like I want to keep the connection open for a while so that latency is lower. I make this change on my own side. Your code doesn't change. You just rebuild it. So that's my perfect world. Sidecars are like slightly less than halfway there. I would say 40% there. But the beauty of sidecars and the modern microservice architecture is that, the beauty of sidecars in the modern cloud architecture, cloud microservice architecture, is that there's always service discovery. So you talk to my service, not by hard-coding my IP address or my internal DNS name. You talk to my service by first requesting the name resolver service discovery component. Hey, I'm going to need to dim a service. How do I reach it? And this service discovery component tells you how to talk to me, and you talk to me through this service discovery's recommended route. So in this world, if you have a sidecar enabled, I can move part of my code from my service to something running on your machine. And it's a DevOps task. As in, your code doesn't change. You don't even need to rebuild it. On the level of cloud configuration, when you want to talk to me, to my service with some protocol, on the name resolution level, I would know that that machine, that physical box you're running on, or that Docker container that you build in, this thingy already has my client library built in. So my service just resolves a local host to you, and your network call is going to your locally running daemon that I'm shipping. And this protocol between these two parts is my internal protocol. It's my team maintaining both my component and this sidecar. So I have a better sidecar. It's faster, it's more reliable, it caches more stuff, it keeps connection open, like long-lasting binary. You don't notice it because your code just works without even rebuilding the code. The last part is questionable because rebuilds are presumably quick these days. I just had to mention this. So yeah, I don't think this is important enough to try to memorize, but my point is that like making a full end-to-end call from your service to my service is like level 0. Full all-in client API that I also maintain with statically checked at compile time signatures is like level 2. Sidecar is level 1, and it's a good enough level for many practical purposes. So yeah, if you design in microservices and you refuse to consider sidecars, you're doing something wrong. In fact, I think it's almost automatic for most architects these days to ask, all right, if we do it this way in our cloud architecture, can we use a sidecar tomorrow? Does our design support moving to a sidecar? When it comes to anything that is potentially high load or highly available in the future, if you design your system without thinking of sidecarring its interface in the future, you're not thinking deep enough. Last slide on best practices. Continuous deployment. there's a trend towards deploying things faster. Like there's even trunk development, which means everything you push to the main branch automatically goes to maybe 1% of the users, like right away from production. I'm not against it. It's an awesome idea. Test your stuff in production. Every company has a test environment. Some companies have a dedicated production environment. So when your production is test, I'm perfectly fine with that. Don't get me wrong. That's all good. The truth is, at some point, deploying faster becomes fetishism, in my practical experience. How often do you really need to deploy? Do you really need to deploy every 2 hours just because you can? I doubt it. In practice, deploying once a week is oftentimes more than enough. BAU here in this slide stands for business as usual. So BAU is the opposite of emergency. We're recording this late December, so it was 3 days ago when the famous Java login library had a huge issue, which potentially could take down the whole internet. Java runs on billions of devices became a curse. The point is, sometimes you need to deploy things fast. If the only process your company has of deploying things takes a week, that's bad, because an emergency might happen and you need to hot patch all of your fleet, in which case you either do it manually, which is error prone, or you have some means to quickly roll out the code to all the machines. Good. Emergency responses have to be designed, tested, practiced, and yeah, all good. But if it's business as usual, like, you need to carefully answer for yourself, how often do you really need to deploy your changes? Comment from a good friend here: if you have to support long-lasting connections, video streaming is an awesome example. It is actually really hard to switch IP addresses on machines when you stream a video, especially if it's like being recorded and streamed live. In most companies I know of, I don't know of many, frankly, but in most companies I know of that do these things, the policy is quite simple. If a machine is running on a live stream, we're not going to take it down. If your live stream takes 72 hours and we need to roll out the new version, if we have 100 machines, maybe 1 or 2 of them would still be up and running 72 hours after we did the full release cycle, because we don't want to interrupt those connections. People would lose the continuity of their experience. So, like, in this world, even if you can deploy every 2 hours, do you really want to? It's in the cloud. You can always spin up more machines, so keep the older ones running for longer. Then the next question is, do you need to deploy everything? If it's truly microservices, chances are different components have different cadence of deployments. Maybe some core pieces you can just deploy once a month or twice a year because they're just simple enough, like some high-level intelligent routing rules with some basic anti-denial of service protection, with hot pluggable rule lists which you can just change on the fly with no restart. This thing can run for years of uptime with no reason to restart it. So what's the point in claiming that we can restart this thing now 10 times a day because we can? No point. Or like if you have a front-end plus backend, a simple web app, you can probably deploy front-end multiple times a day, but the backend just once or twice a week. Sounds fair to me. And then the related question is, if you're honest with yourself and you know it's okay to deploy not too frequently, what's wrong with the build and test taking like an hour? A lot of companies are trying to argue that our build is so slow, we need to speed it up. It's taking more than an hour. My answer is, so what? It's one thing that you're making incremental changes to your code. You're working with your particular microservice code and you're running local tests. Yeah, for this, one line change of more than 6 minutes is absurd, I agree. Ideally, it should be seconds. In many languages that are interpreted, Python, JavaScript, it's fair to expect it to be a momentary change. You can run the test right away. That's fine. But for the whole end-to-end pipeline that builds all the containers and carefully stages them in the right order and runs some tests before flipping production, an hour is oftentimes just fine. If you only deploy once or twice a week, it's okay if you start deploying like 4 a.m. and by 5:30 a.m. it's deployed. That's perfectly fine in production. There's no reason to argue that you should do it differently. So yeah, I'm not saying you should always push back for slower cycles. No way. But I do think it's important to not let dogmatic thinking of we can do it faster. This thinking should not make it to your ultimate decision-making process. Data dictionary schema evolution, yeah, that's again one of my personal pain points. So I'm fully aware I'm biased towards strict schemas. I'm not claiming it's the right way to do stuff. I just hope the world gets there. So I have vested interest, take it with a grain of salt. But my point is, the closer you get to the core data, such as like user metadata or authentication tokens internals, the closer you are to the core data, the more painful it is if you let people put some random stuff into those API calls, into those JSON fields or whatnot. The stricter you are, the better, honestly. On the other end of the spectrum, like something goes, if you're an e-commerce site and some metadata goes to the data warehouse for data analysts to research, and you suddenly have some new field there because you think it might help, like screen resolution in the browser at the moment the checkout happened, put it there. It's not going to hurt. It's cheap to store it, and maybe there's some insight to be found a year later. By all means, I'm not going to argue that you should not put it there. But if it's a core part of the system that has to be high performance, low latency, and highly available, I strongly recommend strong schema. Many solutions these days exist for schema evolution. Schema on read, schema on write. It can be a separate dedicated episode, but the main point is that when people tell you, I want it to be schema agnostic, I recommend running away with a speed inversely proportional to how closely you are to the core data. The closer you are to the core data, the faster you run away from those people. It's just not how things scale, really. In practice, you always want to maintain something like a DAG, directed acyclic graph. So, like, you know who depends on whom, and in this huge diagram of squares and arrows, there's no loop, because loop here would mean circular dependency, which is impossible to resolve without breaking it. And for the final point, I know it's a very controversial topic, but I had to put it here because I believe in it. First of all, there's nothing wrong with multiple services in one repository. So there's a word Monorepo, which I frankly don't see anything wrong with it. If you want to go advanced here, the problem is that, how do I phrase it nicely? The problem for Monorepo is that Git took over. Git is awesome. Git is really good when you have multiple people working on multiple things at the same time, and these things are not connected to one another, which is, surprise, a Linux kernel, which is what Git was built for. In a huge company like Google, it's really hard to use Git because the process big companies have, forget the word Google I said, I don't even know what they do these days. But in practice, if you have a huge company and components talk to one another, oftentimes multiple branches become a pain. You want to have a single like main branch, like thick, like a huge stem where everything goes layer by layer, and you have small branches that quickly get back merged or forgotten forever. That's just not what Git is good at. You have a multi-gigabyte repository. Git doesn't handle it how you would like it to handle it. But forget Git. What could possibly go wrong if you put three services into one repository? I frankly don't see any downsides except for slightly increased checkout time, like git checkout and git clone. If they don't talk to one another, if the code on different directories doesn't touch one another, there would be no merge conflicts, no nothing. You just have a copy of the other team's code. But then, let's say the services need to talk to one another. They have some API spec. They have some TypeScript schema or Java protocol definition or protobuf files, the proto.trif.avro. If you keep these files in the same place as both services, you live in a perfect world because you change them in one place and the build breaks, and the teams which builds broke have to fix it on their sides. Wonderful. If I say to you, hey, I'm going to need something else from you, you make a commit that adds this. I merge with your branch where this thing is added. I build my own thing, and we make a combined pull request into the main branch. where you can see the history that you added this because I asked for it, and I'm using it in the next commit, and the history is perfectly reconstructible as opposed to multiple services talking to one another. And then, of course, since indirectly every service talks to every other service, logically, this religion takes us to one huge repo with a top-level directory for protocols, for message formats, for stuff like that, and then a subdirectory for each service, which honestly I think is often a good thing to have. I've spent many long hours arguing about this, won a few fights, lost a few fights, but there's really nothing wrong with this. Another argument people often use is, oh, why would you ever mix different languages in one repo? So what? It would actually decrease the chance of these languages not colliding with each other. If it's like Go and Go, we might commit the cardinal sin of using each other's internal data structures. If it's JavaScript and C++, there's zero chance we're gonna intersect. So there's actually no pain at all at combining this in one single repository. So why not? The compromise solution, the middle ground, is to have multiple repositories per component with a high-level repository that takes these ones as submodules, Git submodules. We all know Git submodules are not great. There's no need to talk about this. I actually think the solution is often better for a simple reason. It allows running tests across different versions of different services. So if you have service A and service B as subdirectories A and B of the same repo, and we're developing them concurrently, and I want to test A today against B a month ago, I would need to clone the repository twice and then make some symlinks or copy files over, which is painful. If there's a different repositories and then a high-level repo with submodules, you can change the commit hash of a submodule, reclone it, go to the right commit branch or whatnot, and run your tests. So that's actually, I think, the cleanest way, to be honest. Some final thoughts. That's actually the last slide. Again, it's a fairly advanced topic, and I don't start from it in most cases, but you guys have been around for a while, as well as I assume the audience of this. So when things do get to the high level of, like when a conversation about microservices gets to a high level, someone, I believe, must stand up and say the following thing. Hey guys and gals, aren't you aware microservices are not about physical machines, containers, virtual machines, pods, Kubernetes, or whatnot? It's not how the term even started. The idea of a microservice is that you have a subcomponent that is logically disconnected, logically detached from another component. Logical detachment, logically speaking, technically speaking, means one thing only. There's no synchronous call. There's no way to synchronously call B from A. We call as asynchronous, and by the time when A calls B for something, by the time B returns back to A, other part of the system may have changed in some other way. So if you design your system embracing this, if the only way the best way you found for your system to work is to actually depend on the independency of parts, then technically you are building microservice architecture. The corner case example that is absolutely true is high frequency trading, HFT. Unlike companies like Google and Netflix or Apple, you don't really see blog posts from HFT people often. They're busy making money and spending it. That's just mindset issue. I've spoken with tons of them, have good friends. It's just the culture is different. The attitude is different. The approach is different. But in the world of high frequency trading, you would often have a component that needs to have some machine learning models in memory and the caches to apply those things. Order book maintenance, so that once you receive the orders from other components, from the market, from the exchange, you can build your own order book to predict how much weight is there to buy or to sell at different price points for different securities, tickers or whatnot. You have real-time updates of those machine learning models. You have some parameters of which percentage of traffic to use. By traffic, I mean money, of course, of your capital. So, and of course, it has to be super high performant, super low latency. So what you end up having is you buy in the cloud, or more often physically, you buy a super expensive beefy machine with hundreds of cores, like an enormous amount of memory, SSDs if you need those, multiple network cards, connected to different parts of the different exchanges, maybe with different virtual private networks or stuff like that, like custom drivers of those network cards so that they can begin analyzing bits before the packet is fully received. Not kidding. In order to maintain this, what you would have is a single binary. That is the kernel OS binary init image of this oftentimes Linux box. But internally, it's going to utilize all those hundreds of CPU cores. It's going to have thread affinity, so some things are too important, so they are being attached tied to specific thread CPU cores physically forever. They don't change cores. And you have dedicated a couple cores for some data crunching, a couple cores for machine learning models application, a couple cores for whatnot. And you have a perfectly designed and architectured microservice running on this cluster of hundreds of cores, even though it's a single physical machine. So in my head, it's going to be in one repository by far, like absolutely. It's going to be developed by multiple people, one repository, one physical machine, totally microservice. In fact, I would go as far as saying that as long as there is no such thing as before and after moment X in time, so as long as you cannot pause the system and say, hey, this is T0, I have before T0 and after T0. If your time in the system is not describable by a single number, like time, but you need a vector clock, multiple components with their respective time counters, like a Lampert clock, a vector clock is a good term. Once you're thinking in these terms logically, you get to all this exactly once delivery, message brokers, transactions, which exactly is microservices. It was a long detour, but the point is microservices as a logical development concept is not one-to-one connected to microservice as in Kubernetes pod. And it doesn't have to. It literally, like these two concepts are tied together in the hands of many these days, which again, when we're talking about companies hyper-growing and hiring sub-senior people, that's perfectly fine. That's a good heuristic. That's how brains work. That's how humans operate. But those of us who have to work with this at a higher level, I think it's important to understand that microservice does not mean a pod, a virtual machine, like isolated, disconnected. And again, the monolith, let's make it a smoother transition. So I talked about what microservice is. Let's not talk about what monolith is. Let's talk about what is bad in the monolith, because it's easier. And ironically, what is bad in the monolith is bad universally. It's just these are the sins that are easier to commit within a monolith. The most common bad practice is spaghetti code, of course. Monolith just makes it easier to write spaghetti code where component A can look into the internals of component B. Like literally, you have like a large Java application, and component B has some cache. There's some hash map. Like keys correspond to users or pieces of content, and value has something you need. And it's so tempting from your component to go to this cache, maybe even use this mutex that guards this cache. That's the wrong pattern. It's just easier to build things this way if it's a monolith. It doesn't mean if you use a microservice-based architecture, you would never make this, you would never commit this sin. It's good to never ever do it, regardless of whether you are in the world of microservices or in the monolith. So just don't, like abstractions work. Don't use the internal knowledge of some other component, even if you build it and you know this. Assume you may need to move it out as a separate service tomorrow. Another huge pain point is asynchronicity. So if it's in the same machine, if you can make a function call, method call, that's of course in nanoseconds. If it's multiple machines, even if it's localhost network call, you certainly get into hundreds of microseconds. If it's neighboring machines in the same rack, you still can be sub-millisecond. If it's multiple machines in different availability zones, you get to milliseconds. If to serve a user request, you need to make 100 callbacks and get those responses back. 100 callbacks of 1 millisecond is already like 1 millisecond latency. So if it's 1 millisecond one way, then it's 2 milliseconds back and forth. 100 times is 200 milliseconds. The bottom line is, it looks totally harmless if it's within a single process within a single binary within a single machine in memory, it suddenly becomes extremely painful once it's converted into microservices, even though the conversion is done perfectly well. You just change the methods into remote procedure calls. So the answer is, of course, simple. When you're writing the code that is making a synchronous call, a call that is asynchronous, think ahead about the time when you need to make it asynchronous. Think of maybe this method would return you a promise, which will be resolved in the future. This future could be a millisecond later, or 10 milliseconds later, or 100 milliseconds later. Can you do more work on your side to prepare for this promise to return? If you're doing something like a graph traversal, like a example from this week, folder tree traversal, check permissions on the top level folder. If your permissions on a lower level folder are inherited from all the top level folders, then the request to check permissions may have to go multiple steps up, potentially an important number of steps up. I could give you 100 or 1,000 levels of hierarchy. If it's a synchronous call to another service, then any person who made 1,000 directories, like folders, one in another in this product, will be screwed once we replace this permission checking part from this monolith to a microservice. So, and it's not wrong, it just calls for different thought process. Maybe you need to put this cache of permissions closer to this component. Maybe you need to push the data here. This level of thinking, you may well think in the same terms while designing it in the first place, not even thinking about microservices. Just think about, what if this call is suddenly slower? What if it's asynchronous? What can I do to optimize this? Yeah, and the third bullet point here is monoliths oftentimes have slower build times. We talked about this before. I don't want to get back to it. The point is, I'm not trying to defend the monolith. I'm just trying to argue that it's not as black and white as people think it is. If it's a monolith of multiple components, for example, they have properly configured cache for builds, it can build as quickly as all the microservices because, well, yeah, it's just every single component builds by itself. Then they get linked in together. The good lessons we can learn from monoliths is, I spent some time talking about sidecars before. Well, if it's a monolith, you pretty much already have sidecars, because a properly built monolith, when my part of code talks to your part of code, and if I'm trying to do things right, I would not look into your internal data structures. I would talk to you personally, human to human, and ask you, hey, I need that. How do I best access it? And you would tell me, hey, I make a API call for you. You can just call this method asynchronously, ideally. Well, that's your sidecar. It's concealed within a monolith, but people who think in these terms, they already think in sidecars. And when later on you need to break this monolith into microservices, if people were thinking along these lines, they kind of have the API specs ready, and the sidecars come natively. Database transactions, a lot has been spoken about this. Basically, if you're doing two-phase commits, you're doing it wrong, especially if you can afford to avoid two-phase commits by sharing database. Monolithic services that do use one database natively don't have this problem. So, like, by accident, they're doing it right. I'm not saying you should always have one database and all the services talk to one database, but I do think that using the database correctly, using the database abstraction correctly, implies thinking, what can it do that is more expensive to do otherwise? And if it's some database transaction that affects multiple parts of data, pieces of data atomically, simultaneously, well, that's a reason to use a relational database, an RDBMS, and offload this task to the database engine. It pays off in the long run. And yeah, keeping the API specs and the data schemas in one place. If you have a Monorepo, chances are you're doing this part right, because you have a Monorepo and the monolith. So yeah, again, good things have to be learned from multiple places. I think that's it. I was really trying to speak slower today. Like, I was trying to be more relaxed. But on the other hand, I wanted to fit this whole thing into 1 hour, so probably I was speaking as fast as usual. But hopefully you guys enjoyed it. There must be some questions, I'm sure. Or are we done? That's even better. Thank you so much. Happy upcoming new year. Talk to you soon. Cheers.